Today we start well order set. Well order set. We first start with definition of well order set. Definition of well order set. We write this definition. A set with an order relation is set A with an order relation. It's said to be well ordered. It's said to be well ordered if every non-empty subset A, if every non-empty subset of A has a smallest element, okay. Next we give some example of well ordered set. Example, trivial example, 1 2 Cartesian product of Z plus in the dictionary or in the dictionary or array. Okay, here a1 a2 an, here a1 a2 a3 dot and b1 b2 b3 dot with understanding that each element is less than every element to the right of it. Okay, each element is less than every element each element is less than every element to the right of it, okay. Now start this one. Here if we take any subset, we get a smallest element, so this one be an well ordered set. Okay, it is a subset of the sequence b1 b2 bn, then there is an smallest element, and also if C contains any of the elements an, then C has a smallest element. Now 2, this one is example 1, this one is example 2. Z plus Cartesian product Z plus in the dictionary or array, okay. Then Z plus Cartesian product Z plus have a smallest element, okay. Any subset we taken from Z plus, then we get a smallest element a0 b0 if we take, okay. Then Z plus Cartesian product Z plus b and well ordered set, okay. Next, the set of integers is not well ordered in the usual order. Z set of integer is not well ordered, okay. Why? Because the subset negative integers has no smallest element. The subset negative integers have no smallest element, okay. So we discuss a well ordered set. Now we we also discuss about several result about well ordered set. Okay. Now A is a well ordered set. A is a well ordered set. Then any subset of A is well ordered. Then any subset of A be well ordered. Okay. Now in this restricted order relation, okay. In this restricted order relation, if A is well ordered set, then any subset of A is well ordered. And also now we'll also discuss about that. If A, B are well ordered set, then a Cartesian product B is well ordered in the dictionary order. If A, B, be a well ordered set, then a Cartesian B be well ordered. Well order means every subset of A each has a smallest element. Okay. And if every subset of A has a smallest element and every subset of B has a smallest element, then every subset of A Cartesian product B has a smallest element. Now we discuss one theorem, important theorem. We'll first write this statement about theorem. Every non-empty finite order set, every non-empty finite ordered set, set has the order type of a section, has the order type of a section of Z plus a section 1 2 n of Z plus. So it is well ordered. So it is well ordered. Okay. So how we prove it? Every non-empty finite order set has order type of a section 1 to n of Z plus. So it is well ordered. Now we first we show that every finite order set A has a largest element. Every finite order set A has a largest element. Okay. Now if A has one element, then this is trivial. Supposing it for sets having n minus 1 element. Supposing it true for sets having n minus 1 element. Having n minus 1 elements, let A have n elements. Let A have n elements. Then and let A0 belongs to A, and let A0 belongs to A. Okay, then A difference A0, then A difference A0, that means contain n minus 1 element, has a largest element, A1, and the larger of A0 A1 is the largest element of A, is the largest element of A. Okay, now second, how we prove second portion. That means first we show that every finite order set has a largest element. Okay, next second we show there is an order preserving bijection of A with with 1 to n for some n. Okay, then now erase this portion. Every non-empty finite order set has order type of a section of 1 to n of z plus, so it is well ordered. We have to prove that it is well ordered. Okay, so we start with this. If A has one element, then the fact is trivial. How? Then there exists a order preserving bijection A with 1 to n for some n. Okay, that means n equal to 1, then this one is trivial. Now we suppose it is true for sets having n minus 1 element. Suppose that it is true for sets having n minus 1 element. Let B be the largest element of A. Let B be the largest element of A. By hypothesis, there is an order preserving bijection. By hypothesis, there is an order preserving bijection there is an order preserving bijection if dashed a difference b to 1 to n minus 1. Define an order preserving bijection by setting. Define an order preserving bijection if a to 1 to n by setting fx equal to f dash x for x not equal to b and fb equal to n. Okay, so we get also there is an order preserving bijection a with 1 to n for some n. Hence we prove that every non-empty finite order set has the order type of a section 1 to n of z plus each. It is well order. Okay. Now we discuss about that z. Now we discuss about x equal to z plus Cartesian product z plus Cartesian product z plus Cartesian product z plus equal to z plus whole to the power omega. Okay, of z plus with itself, then a1 a2 an less than b1 b2 bn for some n greater than equal to 1, ai equal to bi for I less than n and an less than bn and an less than bn. Okay, now unfortunately it is not a well ordering an order relation on a set x, but it is not well. This is an order relation but not well ordering, but not well ordered. Okay, why not well ordered? Because consider, where is these things, this portion, where it is now, then we start this one. If x equal to 1 1 1 2 1 1 okay, then here exactly one coordinate of x equal to 2 and others are 1, then a has clearly no smallest element. Okay, then the set A has clearly no smallest element. That means A equal to set of all elements x of capital X where small x is on the from this one. Okay, then the set A has no smallest element. A has no smallest element because x is defined as exactly one coordinate is 2. Exactly one coordinate is 2. B2. Okay, so A has no smallest element. Now we're discussing well ordering theorem. if A is a set, if A is a set, there exists an order relation on A that is well orderly. There exists an order relation on A, an order relation on A that is well orderly. That is well orderly. Now we start with this, and also a corollary. There exists an uncountable well ordered set. Okay, corollary, that means uncountable well ordered set is possible. A set there exists an order relation A that is well ordering. Okay, obviously corollary. There exists an uncountable. There exists an uncountable well ordered set. Z plus. Z plus is countable. Sorry. Uncountable means, which is, that means if R difference Q, okay, R difference Q greater than equal to 0, then this one is uncountable well ordered set. Okay. Now we discuss the definition of section. Definition. Let X be an well ordered set. Let X be an well ordered set. X be an well ordered set. And given alpha belongs to X. Let X is alpha. Let is alpha denoted by the set is alpha equal to X such that X belongs to X and X less than alpha It is called the section of X. It is called the section of X by alpha. The section of X by alpha. Okay. Now we going to an lemma. So we erase these things also. This portion. Now we write this statement of the lemma. There exists a well ordered set A. There exists a well ordered set A. Having a largest element. Having a largest element such that the section of A section is omega of A by omega is uncountable, is uncountable, but every other section of A is countable, but every other section of A is countable. Section is omega of A y omega is uncountable and every other section of A is countable. How we prove it? We begin with an uncountable order, well ordered set B. Prove. We begin with an uncountable well ordered set. Well ordered set B. Let C be well ordered set. Let C be well ordered set 1 to product B in the dictionary order. In the dictionary order. Then some section of C is uncountable. Then some section of C is uncountable. Uncountable. Okay. C be a well ordered set, this one in dictionary order, then some section of C is uncountable. Indeed, the section of C by the elements 2 multiplied by B is uncountable. Then let omega be the smallest element of C, be the smallest element of C, smallest element of C, for which the sections of C by omega is uncountable, for which the section of C, the section of C by omega is uncountable. Then let A consist of this section along with the element omega. Then let A consist of this section, consist of this section along with the element omega, along with the element omega. Okay. Let A consist of this section along with the element omega. Then we get the section x omega of A is uncountable and every other section of A is countable. Okay. Next, if A is countable subset of S omega, then A has an upper bound in S omega. We erase this lemma or this portion. Then we start one theorem, which theorem says that if A is a countable subset, if A is a countable subset of S omega, then A has an upper bound in S omega. Then A has an upper bound in S omega. Let A be countable subset of a proof. Let A be countable subset of S omega. For each A belongs to A, for each A belongs to A, the section SA is countable. The section SA is countable. Therefore, the union is also countable. Therefore, the union B equal to union A belongs to A is A is also countable. Is also countable. Since S omega is uncountable, since S omega is uncountable, then the set B is not all of X omega. Then the set B is not all of S omega. Is not all of S omega. All of S omega. Okay. Let X be a point of S omega that is not in B, that is not in B. Then X is an upper bound. Then X is an upper bound for A. And for if X less than A, for if X less than A, for some A in A, for some A in A, then X belongs to S, then X belongs to SA, and hence to B, hence X belongs to B. So contrary of our choice. Okay, then X be a point of this that is not in B. This one is not possible, so contradiction hold. Okay, then X has an upper bound in S omega. Okay, then obviously X has an upper bound in S omega. So today we stop here.